For our math warm-up today, we need to think about or look back at the quadrilateral hierarchy lesson and poster if you have that available to answer these 4 fill-in-the-blank statements. So if you would kind of look back at that lesson and see if you can fill in the blanks for each of these statements. And remember, there may be more than one correct answer. So go ahead and pause your video and do that now. Okay, so if we take a look at this first statement, every single square is also a blank. So for this particular statement, you could have filled that in with kite, rhombus, rectangle, trapezoid, quadrilateral, or even parallelogram. Hopefully you got one of those. For our second statement, a kite is always a blank. For this one would be quadrilateral. Okay. Last statement, all blank are also parallelograms, but not all parallelograms are blank. So let's start with this first blank. All, we could have squares, rectangles, rhombuses, either of those 3. And then, of course, that's going to change your answer here depending on what you chose. But you could have had squares, rectangles, or rhombuses in this blank. So let's take a look at our math message today. For this particular lesson, it is all about a pendulum. So you're going to take a look at page 311 in your math journal. And if you have these items that I've listed here off to the left to do this lesson, we're going to see if we can make our own pendulum. So let's read about what in the world is a pendulum. And hopefully, as you look at this clock here, that might give you an idea. A pendulum consists of an object called a bob suspended from a fixed support so that the bob can swing freely back and forth. You might have seen a pendulum on a clock. According to legend, the Italian scientist Galileo began investigating pendulums in 1583 after he watched a hanging lamp swing back and forth in a cathedral in Pisa. Galileo discovered that each swing of a pendulum takes the same amount of time, so he began using pendulums as timing devices. Later, his findings led Dutch mathematician Christian Huygens to invent the first pendulum clock. Imagine that you have 2 pendulums, one longer than the other. Do you think the 2 pendulums would take the same amount of time to swing back and forth? Or would one have a longer swing time than the other? Explain your answer. So this is kind of like science where you're making a prediction about what you think is going to happen. So go ahead and pause your video, complete that activity in your math journal, and come on back when you're ready. So your lesson today is pendulums, and it's all about place value, grids, and graphs. And there's actually 2 parts. We have a part 1 and a part 2, but we're only going to do a video for part 1. Why we're doing this lesson today is we want to be able to mentally divide for simple division problems, which I'm sure all of you will be able to do. And we want to accurately graph data collected. And how we're going to go about that, we're going to conduct some experiments with a pendulum. So you'll notice I have several things here on this particular part of our video. Up at the top we have directions and preview. So I am going to have you watch a video that you're going to need to complete some of the information here on your workbook page. So you'll need to have your workbook page open, kind of preview that for a minute. Notice at the top it says that your teacher is going to demonstrate an experiment with a pendulum that is 50 centimeters long. So we're going to use that video that I have moving around here to kind of do that little experiment.
A pendulum is simply weight suspended from a pivot such that it can swing freely. A pendulum moves to and fro about a point, and hence it shows oscillatory motion. The time taken by a pendulum to complete one oscillation is called its time period. Let us calculate the time period for a given pendulum. Here we have a pendulum and a stop clock. Now we will count the time it takes to complete 10 oscillations. Swing the bob to one side and leave it. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Oscillation is a motion that repeats itself regularly, so it took 13 seconds to complete 10 oscillations. So the time period for the pendulum is 1.3 seconds per oscillation. Now we have shortened the length of the pendulum. We will see the effect on the time period. Let's swing the pendulum and start the stop clock. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now it took 8.5 seconds to complete 10 oscillations. So the time period for the shorter pendulum is 0.85 seconds per oscillation. Hence we note that the time period of a pendulum depends on the length of the pendulum.
Okay, so that was, the video there, and I don't want to start another one, so I'm going to try to move that one out of the way so we can take a look at your workbook page there. Okay, so if we take a look at number 1, it says record the time it took the pendulum to complete 10 swings in 50 centimeters row at the table at the bottom of the page. So basically I'm going to have you take the data that you were able to collect from that video, and you might need to go back and rewind and watch it again if necessary. And then it's going to give you some directions. So we're just going to do the best that we can to fill in what we're able to use from that video clip to complete this activity today. And then we may end up adding some data in class if you don't have enough. So be sure to read all of the directions here and fill in the best that you can for the table down at the bottom. And then once you've completed that information, then comes the time to go to the next page, which is 313, and you're going to write your data from the table on 312 in pairs. So basically you're making ordered pairs here, and then you're going to plot those in the line plot graph here. So hopefully that will make sense. This is not a new concept. You have been doing coordinate grids and graphing for quite some time. So it should just be practice for you. And to summarize today's lesson, this lesson will allow us to practice graphing information and analyzing data. Until next time.